After studying this module, you shall be able to revise the basics of inferential statistics, learn about the basic concept of hypothesis testing and the steps involved in it, evaluate different types of statistical tests used for testing hypothesis about means, learn about the single mean Z test, learn about the single mean T test, learn about the factors that influence the Z and T statistics. Inferential statistics. Population is a large parameter that cannot be subjected to direct measurement. So, we often make an estimate by drawing a sample from the population that gives us information about the likely value of population parameter. This process of generalizing the conclusion about the characteristics of population by collecting the data on a sample which is derived from the same population is called inferential statistics. This branch of statistics helps us to test whether the relationship we found in our sample data is the same as the relationship we would find if the entire population is tested, or the relationship in our sample data is just a coincidence produced by sampling error. For example, let us say that a researcher wanted to know the average mathematics score of the 5th grade boys. What he might do is take a sample of 100 5th grade boys from a local school and record their mathematics score obtained in the final term examination. He could use the average mathematics score of those 100 boys, a sample estimate, to make a guess about the average mathematics score of all the 5th grade boys, a population parameter. Hypothesis. Hypothesis testing. Statistical inference about a population parameter can be done by hypothesis testing. It is a statistical tool that predicts relationship amongst the variables under study. The null hypothesis makes a specific claim about the variables and is a statement of no relationship amongst the variables. The alternative hypothesis simply says that the null hypothesis is incorrect. It is important to note it is only null hypothesis which is subject to reject or retain in hypothesis testing. If null hypothesis is rejected, there is no reason to believe that the alternative hypothesis is supported. Further, the decision to retain the null hypothesis does not mean that it is likely that it is true, but only that it can be true. Thus, we use the term retain the null hypothesis rather than accept it. Using the same example as above, the null hypothesis may be stated as that there is no significant difference between the average mathematics score of the sample and the population. The alternative hypothesis can take two different forms. The null hypothesis is false, that is, the average mathematics score of 5th grade boys in sample is not equal to that of the population parameter. This is called the two-tailed hypothesis, as we find that we can reject the null hypothesis in the upper area of the normal curve, as we shall see, and in the lower area itself. The average mathematics score of 5th grade boys is greater than or less than the population mean. This is called the one-tailed alternative hypothesis, where we reject the null hypothesis, or the null hypothesis is not accepted because either it is the average score, as we have been discussing, is greater than the population parameter or less than. Either of the two has to be true. So, there are two possible alternative hypotheses in this case, right. Such hypotheses are called as one-tailed alternative hypothesis. Let us look into the steps involved in hypothesis testing. The hypothesis testing involves 6 basic steps, and in testing them, the 6 basic steps involved in the testing of statistical hypothesis in inferential statistics are stating the null hypothesis, stating the alternative hypothesis. Now, this alternative hypothesis can be directional or non-directional, as we just discussed. Setting the decision criteria by specifying the alpha level of significance, collecting the data and evaluating the null hypothesis by determining the standard error of mean and calculating the test statistic, which can be Z or T, as we shall see in the coming sections. And then finally, stating the conclusion about the null hypothesis. We shall follow these steps of hypothesis testing in the coming sections of this module. Hypothesis testing about means. Different parametric tests are used to test a hypothesis about means. The 3 commonly used statistical tests for testing hypothesis about the means are Z-test, T-test and Anova, which is also called as analysis of variance. The test applied to a particular statistical hypothesis depends on the number of groups involved in the study, the purpose of hypothesis testing and other statistical measures available in the hands of the researcher. So, which particular test Z, T or Anova has to be used depends upon the research design and a number of other factors prevalent. The following table depicts the details about the application of Z-test, T-test and Anova. Let us have a look. We can find that the 3 tests vary in their application on the basis of the purpose of the researcher, the groups that we have, that is the number of samples which are involved in the study, and of course the sample size and statistic of population. The Z-test is used when the purpose is to compare the sample and the population. There is one group involved, we prefer a large sample size and the standard deviation is known. The T-test on the other hand is used when the purpose is to compare a sample with the population for one group and the standard deviation is unknown. The purpose of the Z-test can also be for comparison of 2 means with the large sample size and a known standard deviation, and in such cases there can be variation of between subjects and within subjects designs also. The T-test again can also be used for 2 samples, and again we may have a between subjects design or a within subjects design, as we shall see in coming section. The Anova, however, is a more different one. Here there may be a comparison of multiple samples, that is, in those cases where there are more than 2 samples involved in a particular research, then a researcher would definitely prefer the Anova or the F-test to compare the means among the samples. The current module discusses single mean Z-test and single mean T-test as used in experimental design. Let us start with the single mean hypothesis testing using a Z-test. The z-test is the simplest form of hypothesis testing about the means, in which the comparison of an estimated mean is done against a constant value. The aim is to determine whether the average score on a variable in the population is different from a specific known constant. Numerically, a z-score represents the number of standard deviations the raw score is above or below the sample or the population mean. The assumption of the z-test. For testing hypothesis about single mean using z-test, the following conditions must be met. The sample must be randomly drawn from the population. The sample should be drawn with replacement sampling method. The scores are normally distributed in the population. The mean of the population of scores is known, and true standard deviation of the population scores is known. The steps for computing z-statistic. The 6-step method of hypothesis testing using z-score is elaborated below with the help of a numerical example also. The first step is stating the null hypothesis. The null hypothesis, that is HO as we call, is subjected to research inquiry about the population parameter is framed by the researcher. When comparing a mean to a constant using z-test, the null hypothesis will always be that the corresponding population parameter is equal to the constant value. In the example above, if the average mathematical score of the 5th grade boys of population parameter is 80, then statistically the null hypothesis or HO is expressed as HO mu equal to 80. It states that the average mathematical score of 5th grade boys in the sample is 80. Formulating the alternative hypothesis is the next step in hypothesis testing, and we may formulate a directional or a non-directional hypothesis. The alternative hypothesis, that is HA to null hypothesis, is formulated in this step. Identification of region of rejection is done by specifying whether the alternative hypothesis is one-tailed or two-tailed. Statistically, HA is expressed as HA mu not equal to 80. This is a two-tailed alternative hypothesis which is non-directional in nature. It states the average mathematical score of 5th grade boys in sample is not 80. HA, where mu is greater than at 80, is a one-tailed or directional alternative hypothesis. It states the average mathematical score of 5th grade boys in sample is greater than 80. HA mu less than 80 is a one-tailed alternative hypothesis which is directional in nature, and it states that the average mathematical score of 5th grade boys in sample is less than 80. We can have a look at the figure 1, which shows a sampling distribution of HO, that is the null hypothesis, which shows the region of rejection for one-tailed z-test. One-tailed z-test means the alternative hypotheses are directional here. Figure 1 shows a sampling distribution for null hypothesis HO showing the region of rejection for one-tailed z-test at alpha equal to 0.05. The region of rejections are shown in the dark blue, if you can see, and they are standing for the directional alternative hypothesis, where the region of rejection gets concentrated either in the upper tail or in the lower tail of the normal curve. The figure 2 shows the sampling distribution for HO showing the region of rejection for the two-tailed Z test. One remembers that the alternative hypothesis says that the region of rejection is distributed in the upper tail as well as the lower tail of the normal curve as shown by the dark blue section of the normal probability curve. The next step in hypothesis testing is setting the decision criteria by specifying the alpha or the level of significance. The criterion to determine whether the null hypothesis is to be accepted or rejected, termed as alpha level of significance, needs to be determined in advance. One can see that the level of significance is represented by the letter alpha here. The alpha level of 0.05 and 0.01 are generally used in psychology. So, conventionally we will find that research in psychology opts for two level of alpha values, that is 0.05 and 0.01. In a two-tailed test, of course, the alpha level of 0.05 means that the total area of 0.05 gets distributed in both the tails of the normal probability curve and each region has 0.025 in its individual tail. If it is a one-tailed test, of course, the entire 0.05 region of alpha level of significance gets concentrated either in the upper tail or in the lower tail of the normal probability curve. Let us take an example. Let us assume that the researcher decided to set the decision criteria in the above example to be two-tailed at alpha level of 0.05. And we can see the figure 1 and figure 2 discussing the alternative hypothesis of one tail and two tail levels, how the region of rejection gets distributed in both the tails of the normal probability curve here. The collection of data, of course, is the next step. At this step, data is collected on a sample derived from the population. Example, the researcher selected 100 5th grade mathematics students from a school and subjected them to the test. After the treatment, it was found that the average score on the mathematics test of the sample was 85. Let us assume that the standard deviation was 20 for this chosen sample. The next step is evaluating the null hypothesis by determining the standard error of mean and calculating the Z statistic labeled as Z obtained here. This tells us how different our observed data is from the value under the null hypothesis. The standard error of means is calculated by using the formula standard error of mean, that is sigma x bar is equal to sigma x upon under root of n, where sigma x is the standard deviation of the population and n is equal to the number of subjects in the sample. The Z score for the sample mean is calculated by using the formula Z obtained is equal to x bar minus mu upon sigma x bar, where x is the sample mean, where x bar is the sample mean, mu is the population mean and sigma x bar is the standard error of mean. Let us take an example and see how these steps are followed. Given the values above, the standard error of mean and Z can be calculated as the standard error of mean is equal to the standard deviation 20 upon the square root of the sample size n, which is 100, comes out to be 2. The Z obtained after substituting the values in the Z obtained formula are 85 minus 80 divided by 2, and we arrive at the Z obtained value of positive 2.5. The next step, of course, is to determine the critical value of Z statistic, that is the Z critical. The critical value of Z score that gives the appropriate portion of scores in the region of rejection in the tails of the distribution is seen from the standard table of reference that gives the area under the normal corresponding to the given value of Z. The critical value of Z score is taken according to the prior assumption of one tail, that is the area between mean and Z, or two tail, area beyond Z. And we can read the required value from the table. Here in this case, table area under the normal curve corresponding to the given value of Z are given. We can find these tables available in most of the statistics books, and in this case they have been taken from a statistics book, Clark, Kolodarchi and Caffery, right? And for the Z value of 1.96, the area between mean and Z is 0.4750 and the area beyond Z is 0.0250. Example, for a two-tail test, the corresponding Z critical value will be separated into the upper 2.5% and the lower 2.5% of the sample. Thus, the Z critical value for the two-tail test at alpha of 0.05 is equal to plus minus 1.96. Now, once we have the Z critical and Z obtained values with us, we can state about the conclusion. After calculating the Z score, interpretation of Z obtained is done relative to the Z critical to report whether the results obtained were significant or non-significant. For this, we compare the Z obtained value to the Z critical value. If the Z obtained is beyond the Z critical value, we reject the null hypothesis as the Z obtained lies in the region of rejection, and we can safely conclude that the null hypothesis is rejected and is considered statistically significant. In the example above, if we reject the null hypothesis because the Z obtained of plus 2.5 is greater than the Z critical value of 1.96. Thus, the mathematics score of the sample is not same as that of the other fifth graders in the population, or in other words, we may also say that the difference of 5 points between 80 and 85, that is the population mean and the sample mean, is not because of some error, but this difference of 5 points is a significant difference. If Z obtained is less than the Z critical, that can also be one of the possibility, although not in this case, then we retain the null hypothesis, thereby concluding that no significant difference exists between the sampling statistic and population parameter. Although there might be some difference between the sample and population parameter, but then we attribute it completely to the errors of the sampling and not because of the treatment condition. Let us assume that the researcher decided to set the alpha level of significance at 0.01 level rather than 0.05 for a two-tail test in the above example. Taking the same sample mean as well as the Z critical and obtained values from the standard table of reference, the Z critical value for two-tail test at alpha of 0.01 when the entire 0.01 region gets divided into two tails is plus minus 2.57. The sample mean now falls in the region of retention, and therefore decision would be to retain the null hypothesis. The single mean hypothesis testing for t-test. For computation of z-test, the mean and the standard deviation of the population must be known so that the standard error of mean can be computed. However, in many cases, the standard deviation of the hypothesized or comparison population is not known. For such cases, t-test is used as it estimates the standard deviation from the sample itself. The formula for the t-statistic accomplishes this by substituting S square for sigma square in the formula for the z-statistic. The t-test is commonly known as student's t-distribution or student's distribution of t. Statistically, the formula for calculating the t-test is represented as t obtained is equal to x bar minus mu upon Sx bar, and Sx bar is equal to standard deviation or capital S of x upon square root of n, where x bar of course is the sample mean, mu is the population mean, Sx bar is the standard deviation of sample, Sx bar is the standard error of sample mean, and n is the sample size. Thus, if infinite samples of the same n size have been drawn from the population, then by calculating mu, Sx and Sx bar, t-score can be computed. Assumptions of t-test. Performing t-test, the following assumptions must be hold true. The sample must be randomly drawn from the population. The sample should be drawn by with replacement sampling method. The scores are normally distributed in the population. The dependent variable should be in interval or ratio scale of measurement. Means of the population of scores is known. True standard deviation of the population scores is unknown, so it is estimated using the sample data. Steps for computing t-statistic. First, stating the null hypothesis. The null hypothesis HO subjected to research inquiry about the population parameter is framed by the researcher here. When comparing a mean to a constant using t-test, the null hypothesis will always be that the corresponding population parameter is equal to the constant value. Second is formulating the alternative hypothesis, which again can be directional or non-directional here. The alternative hypothesis HA to null hypothesis is formed. Identification of the region of rejections is done by specifying whether the alternative hypothesis is one-tailed or two-tailed. Next is setting the decision criteria by specifying the alpha level of significance. The criterion to determine whether the null hypothesis is to be accepted or rejected, termed as alpha level of significance, needs to be determined in advance. The alpha level of significance 0.05 and 0.01 are generally used in psychology. In a two-tailed test, alpha level of 0.05 means that 0.025 is divided equally in both the tails of the normal curve. If it is a one-tailed test, of course, 0.05 stays in just one tail of the NPC. Collection of data is the next step, of course, and the data is collected on a sample derived from the population. Evaluating the null hypothesis by determining the standard error of mean and calculating the t-test statistic labeled as t obtained. This tells us how different our observed data is from the value under the null hypothesis. The formula for calculating t-score is represented as t obtained is equal to x bar minus mu upon Sx bar, where Sx bar can be calculated as Sx bar equal to Sx upon square root of n. Determining the critical value of t-score, that is t critical, and the t critical can be the t-score that gives us the appropriate portion of scores in the region of rejection in the tails of the distribution, and this is calculated by finding the value of degree of freedom here. The degree of freedom represents the number of individual subjects data points that are free to vary and is given by the equation df is equal to n minus 1, where n is the sample size. Thus, for 10 scores in a total, degree of freedom will be 10 minus 1, 9, which means that 9 scores are free to vary and the 10th one is fixed. The value of t critical is obtained from the t table, as it is called as the student's t table. The value is taken by matching the df value or the degree of freedom with the corresponding column depending upon prior assumption of one tail or two tail test of significance level of alpha. The table is shown here, and we can see in the first column degrees of freedom are given, whereas the other columns, which are subsequently ranging from 0.25 to 0.005, give the region of or the area that is situated in one of the tails of the curve at a particular degree of freedom. Table 3, students' t distribution, and of course this table can be found in most of the statistical books. The next step is stating the conclusion. After calculating the t-score, interpretation of t obtained is done relative to the t critical to report whether the results obtained were significant or non-significant. For this, we compare t obtained value to the t critical value. Now there are a number of possible outcomes. If t obtained is more than t critical, we reject the null hypothesis because we conclude that the significant difference exists between the sample statistic and the population parameter. The rejected null hypothesis is considered statistically significant. If t obtained is less than t critical, then we retain the null hypothesis, thereby concluding that no significant difference exists between the sample statistic and the population parameter. Let us illustrate all these steps taking an example. A psychiatrist working with the treatment of patients suffering from insomnia claims that his drugs help the patients by getting them into an average sleep of 8 hours a night. To test the claim, the psychiatrist's sleep data was collected from 25 patients. The mean for the sample was found to be 7.2 and the standard deviation of the sample was reported to be 1.5. Now, we had to prove that the drug has an effect on the insomnia. State formally the hypothesis necessary to perform a non-directional test at alpha equal to 0.05 and conclude the findings. Let us do this example, and we find that the null hypothesis states mu is equal to 8, whereas the alternative hypothesis, which is non-directional in nature, states that mu is not equal to 8. We have already pre-selected the level of significance alpha to be 0.05. Now, with the application of the formula for t obtained and the Sx bar, we obtain the t value to be minus 2.667 at the degree of freedom n minus 1, which is sample size is 25. So, the degree of freedom arrives at 24. Now, we can look up the table and we can get our t critical value at alpha equal to 0.05 with a two-tail test to be plus minus 2.064. The t-score observed from our data, which is minus 2.667, falls beyond the critical value. Thus, we reject the null hypothesis and conclude that the drug has an effect on the insomnia. And the difference between the two values of mean is not only because of the sampling error, the drug is influential. The factors influencing Z and T statistics. Various factors that influence the Z and T are: greater the difference between the sample mean and population mean, greater will be the T and Z values. Smaller the value of standard deviation, larger will be the values of T or Z as it decreases variability in our sample error. So, the error goes down. Greater the sample size, the bigger will be T and Z. Smaller the significance level alpha, higher will be the critical Z or to reject HO, T required to reject the HO. Two-tailed test split alpha into two tails of the curve and the probability is less than 0.025 instead of one tail at P equal to less than 0.05. T-tests are just like Z-tests, except that they compensate for the increasing uncertainty of small sample sizes. For very large sample sizes, the T-test approach the Z-test and they are almost identical, as we may look up the table values and find this by ourselves. When the small sample size, students' T distribution is a preferred statistic than Z-test, that is, whenever our sample size is less than 100, we always prefer to use T rather than Z. The curve of T distribution varies with the sample size. That is the reason we take degree of freedom into consideration, which is dependent upon the sample size. The curve of the T distribution is flatter than that of Z distribution, but as the sample size increases, the T curves start resembling the Z curve. Summary: an inferential statistics hypothesis testing is designed to detect significant differences. In hypothesis testing about the single mean, we compare a random sample from a large group to a population. This is done by using Z-test and T-test. Z-test is used in situations where mu and standard deviation of population parameters are known. T-test is used when the standard deviation of the population is not known, and in this, standard deviation of the sample itself is used to estimate the population standard deviation. The 6 steps involved in hypothesis testing using Z and T test are: state the null hypothesis, state the alternative hypothesis of directional and non-directional nature, determine the alpha or the level of significance, collect the data, evaluate the null hypothesis by calculating the test statistic using the Z or T formula, and determine the critical value, and ultimately state the conclusion dependent upon the T and obtained and critical value of Z or T. Both Z and T are affected by several factors, as we have seen